Okay, today we're very pleased to have two members of the research group of Professor Dana Friedman and CDAC partner Steve Jacobson at Northwestern University. This group has been carrying out some fascinating chemistry and has focused attention on the ways in which pressure can promote the formation of new compounds, particularly intermetallic phases. As we've seen in two previous presentations from members of the Northwestern group, they use an impressive array of characterization techniques to bear in order to address structure-property relationships in materials at high pressure. Today, we're pleased to have Allison Altman and Alexandra Tamerius giving the presentations today. So we'll have two separate presentations back to back. Allison Altman is a postdoctoral researcher at Northwestern, and in addition to high pressure synthesis of a variety of different types of compounds, she's also developing spectroscopic techniques for following the formation of and measuring the properties of high pressure phases in situ, which is a challenging task. In addition, she uses computational methods to identify candidate phases for synthesis, but also pursues computational work to understand the electronic structure of matter, as she describes it, from molecules to materials. Allison received her PhD degree at Berkeley in the group of Professor John Arnold, where she studied the interactions between actinide elements and aluminum in heterobiometallic molecules, and also used X-ray absorption spectroscopy to develop electronic structure models for these complexes. As an undergraduate at Yale, Allison worked on the synthesis of organic molecules to serve as linkers for attaching chromophores to titanium dioxide surfaces for use in dye-sensitized solar cells. So she has a wide variety of experience in synthesis of inorganic systems. Allison has also participated in the activities of the Searle Center for Advancing Teaching and Learning at Northwestern to work on approaches to active learning in the undergraduate curriculum. At Berkeley, she served as the head graduate student instructor for general chemistry, which must have been a very challenging assignment. Today, Allison will discuss her work on computationally directed discovery of molybdenum dibismuthide. Allison, welcome.
Hi, great. You can hear me?
Yes.
Cool. Thank you so much, Steve, for that wonderfully kind introduction and for inviting me to talk today. And also just thank you, CDAC, for supporting the seminar and a lot of this research. As Steve mentioned, I'm really excited to be here today to talk to you about our combined computational and experimental approach to the discovery of high pressure materials, particularly in the molybdenum and bismuth system. And this is really the result of a highly collaborative effort. So I want to start off by thanking my co-authors and collaborators whose names are listed here, and maybe you recognize from some previous or soon-to-be CDAC seminars. So let's dive into some science. We're interested in our research group in studying of intermetallic materials, and one of our previous lab mates, James Walsh, gave a really excellent introduction to some of the power of exploratory science that we do to lead to transformative new materials whose applications we might not even be able to imagine as of yet. To complement such efforts, I think it's also really important to make sure that our chemical intuition keeps pace so that we can also simultaneously develop rational design principles. We like to focus on intermetallic materials in our group because they have defined crystal structures. An intermetallic material is a material that combines two or more metals into a ordered structure that is distinct from its constituent elements. That's to sort of distinguish it from, say, an alloy in which you have random substitutions. And in particular, this strong internal order, structural order, is of course going to be related to the types of properties you get out of such a system, and at the same time provides us a window into how such properties arise. In our research group, we like to focus on the types of properties and types of behavior we get from incorporating heavy elements into our system. And my colleague Alex is going to follow up this presentation with her beautiful lead work. So today I'm going to focus on bismuth. And in a lot of ways, bismuth is a great element to work with. It's non-toxic and abundant. It's not radioactive, if that's the type of thing you're worried about. I've done a fair bit of radioactive chemistry myself. But in this case, it's nice to work with such a heavy element that in a lot of ways is synthetically quite easy to handle. And so that allows us to introduce a large source of spin orbit coupling into our systems. And if I just limit myself to my favorite examples of binary bismuth intermetallic, we get a sense for the diversity of behavior such materials might exhibit, from permanent magnetism in manganese bismuth to superconductivity in nickel bismuth and non-trivial topology in sodium bismuthide. And while each of these compounds or classes of compounds is sort of its own body of literature in its own right, which I don't have time to really dig into today, hopefully this still gives you a flavor for the types of really interesting things we might learn if we make a new bismuth material. At the same time, what these materials speak to is how such complex properties can arise from simple stoichiometries and also simple systems. However, a real challenge in the chemistry of bismuth is that it's a relatively not reactive element. And I think this is best encapsulated by this phase diagram here, which is from the literature for molybdenum and bismuth, which is going to be the focus for the rest of this talk. And you can see that these elements stay immiscible in this two-phase region up to thousands of degrees Kelvin, when they both enter the gaseous state. And in fact, this is representative of group 6 element chemistry more generally with bismuth. And by that, I include chromium and tungsten as well. And I think this represents a real gap in our understanding for how things like orbital occupation, electronegativity, and size, all things which define this group on the periodic table relative to its neighbors, are going to influence conditions for reactivity, the structures you get, and their properties. At the same time, what this diagram speaks to is that if we limit ourselves to this temperature composition phase space, we're going to be somewhat stuck because it's already been well explored and found to be empty. And so the answer to this problem might be somewhat obvious given the topic of the seminar series, but in our group, we like to use pressure as a tunable synthetic parameter for accessing new regions of phase space. And as Steve mentioned, I started doing high pressure research for my postdoc position. And I was tempted at first to think of it as mainly a densifying force. But in fact, at geologic relevant pressures, you start to see that the elements of the chemistry of the chemistry of the elements, excuse me, are changed significantly, such that in high pressure phase space, you start to get reactivity and structures that sort of defy our intuition based on ambient conditions. And so this is both an immense opportunity. There's lots of space to explore, but also a challenge because we don't necessarily know where to look. And so somewhat coincident with the start of the pandemic, I was wondering if we could use computations to better direct our synthetic efforts. And as a synthetic chemist, my first thought was that it was going to be a hard problem to predict structures de novo. And in fact, it is. It's a 3n-6 dimensional hard problem where n is the number of atoms in your system, and that quickly becomes an unwieldy number for even the most advanced supercomputers. Fortunately, though, we can apply some constraints based on just some basic physical and chemical assumptions. And I think this is best captured by a toy problem, if you would, of a 1D potential energy surface. And so to be honest, this is totally arbitrary what I'm showing you here. I just sketched it in my favorite graphics editor. But you can think of it as describing two atoms in space where the parameter of interest is just the distance between them. And we don't need to know anything about what these atoms are to already make some assumptions about what we're going to find on this potential energy surface. For example, if there is a stable configuration to be found, it's going to be at the bottom of a potential energy well, where the deeper the well, the more stable the structure. However, there might be multiple of these wells corresponding to local minima as well. Furthermore, we know that as we move those two atoms apart and bring them back together, we wouldn't expect small changes in distance to introduce discontinuities in the energy of the system. That in turn places a limit on the curvature connecting these local minima as well as to this global minimum. And so that has a profound implication on what this phase space looks like. That means that in general, the more stable the structure, the deeper the well that it lies at the bottom of, the larger the amount of phase space that this well takes up. And so that's going to underpin our computational approach. In our case, we chose to use ab initio random structure searching, or AIRS approach, and we were mentored in the application of this approach by one of its founders, Chris Ricard, who has been very supportive in getting this research program in our group off the ground. And so in the AIRS approach, what we are essentially doing is randomly assigning a random number of atoms to a randomly sized box. That's equivalent to dropping balls throughout our 1D potential energy surface. We then perform a density functional theory based geometry optimization, which sends those balls to the bottom of the nearest well. And because of that rough correlation between well depth and the stability of that structure and well volume, if we can sufficiently sample phase space, we have a good chance of discovering the stable structures that we're going to find in experiment. And this is an ideal approach for doing high pressure research because strictly no prior knowledge is required, which is useful when we might not have any intuition for the types of structures we might get. However, that said, we like to start off by imposing sensible biases to our search to ensure sufficient sampling. And so we start off by sticking to relatively small unit cells, introduce some symmetry elements, as well as density constraints. Sort of at a practical level, to encourage you to use this very implementable approach, it's quite easy to include pressure in your calculation. It is simply a variable you set that is included in your enthalpy calculation that goes into the geometry optimization step. And so I applied this approach to my molybdenum bismuth system of interest, and here I'm showing you my results from 0 GPA. I identified over 1,000 converged structures, each corresponding to local minima on the potential energy surface. To compare those structures relative to each other, I looked at their enthalpies of formation and plotted all that information on this diagram here, in which I have formation enthalpy on the y-axis, composition on the x-axis. We're moving from molybdenum on the left to bismuth on the right. To figure out what is the most stable structure in the system, I construct a convex hull, which is a line segment or segment that encompasses all the data. And because of how high in energy all these blue dots are, all these molybdenum bismuth systems are relative to the elements themselves, I only need a line segment connecting molybdenum and bismuth, suggesting that they are the only stable materials in this phase space. And of course, that's exactly what we would expect given that empty phase diagram I showed you on a previous slide. Fortunately, though, by the time we get to 40 GPA, the situation has changed dramatically. We now have multiple structures which have negative formation enthalpies relative to the elements, including 2 structures, this 1-to-1 phase and 1-to-3 phase, highlighted in green, that now define the convex hull, suggesting that they're stable relative to each other. Examination of these structures reveals that they're actually quite similar both to each other as well as to the elements themselves. These are all based off this body-centered cubic, or BCC motif, in which you have a unit cell defined by atoms at the corner of a cube as well as 1 atom at the center. And in fact, this is a really common structural motif throughout this phase space. And I think this speaks to the fact that there is very little energetic preference for placing an atom of a given type on a site in this BCC or distorted BCC type lattice. And so while we limited ourselves in this case to small unit cells as a place to start, I think what we're capturing is actually a tendency towards longer range order or even alloying in the system that would be otherwise rather difficult to get at with these high throughput calculations. But in doing this analysis, I also came across this structure here, which falls at the 1-to-2 stoichiometry. And you can see here that's quite distinct from that BCC motif. This is beautifully ordered structure based on square antiprisms of bismuth surrounding chains of molybdenum that go back into the plane of your screen. And this was readily recognizable as the copper dialuminide structure type. This is a very common structure type. It's shared by over 100 combinations of elements across the periodic table. And very importantly, has also been found for other high pressure combinations of transition metals with bismuth. And so at this stage, we thought we had something of a handle on what we might expect to find in our experiments, although there were still some outstanding questions about how sort of the assumptions that go into this computational approach was going to translate to our experimental conditions. And so at this point, I want to switch gears a little bit to talk about our experiments. And I have a feeling that this audience doesn't need an introduction to diamond anvil cells. And in fact, James Walsh, a couple weeks ago, gave a really comprehensive introduction to our lab's approach to doing this science. So just briefly, I'll mention that in this case, for these molybdenum bismuth reactions, I ball milled the elements together create very well mixed powders. I then press that mixed powder into a thin foil and sandwich that piece of thin foil between two pieces of laser cut magnesium oxide discs, or MgO discs, which I placed in the diamond anvil cell to create this sandwich, if you would, where we have our magnesium oxide acting as our pressure transmitting medium, our thermal insulation for our diamonds, as well as our pressure calibrant. Here's a picture of what that ends up looking like. You can think of it as this being, say, the top diamond in our setup, where we put one laser cut MgO disc, and here's the bottom diamond in our setup, which has a rhenium gasket, which ensures that our samples stay confined, another piece of MgO. And we're going to place a thin foil of molybdenum bismuth onto one of these discs, and then close up the diamonds to create that sandwich. And as I mentioned, we really want to thank CDAC for giving us access to some of these experimental capabilities. It's been wonderful to work with the people at the APS at HPCat. And in particular, I'm going to report results today from working with Yue Meng at HPCat beamline 1690B. And this really amazing beamline is, here's the schematics here. Here's a picture on the right. And at this beamline, we can heat our samples up to thousands of degrees Kelvin with these lasers, while simultaneously performing microdiffraction on the heating spot to rapidly scan through temperature, pressure, phase space, providing the perfect complement to those high throughput computations I showed you on a previous slide. And so I took a diamond anvil cell containing molybdenum and bismuth to HPCat and pressurized it up to 36 GPa, so right around that 40 GPa conditions that I was showing you that I addressed computationally. And hopefully you can see here that by the time we turn on the lasers and get to this pattern here, we start to see the formations of new peaks growing in. So that corresponds to about 1400 Kelvin in terms of temperature conditions. And we can watch how these peaks evolve as we play around with the temperature to try to push the reaction towards completion. And we end up with beautiful diffraction patterns at the end that look like this, with the new peaks highlighted with these green dots. And so we can look at these new peaks and index them to suggest a unit cell, compare that unit cell with the literature to come up with a model, and refine against that model to come up with a candidate structure. And so here is the result of that Rietveld refinement. And hopefully we're immediately struck, as I was, the similarity between this structure, which is derived from the experiment, and the computational structure I showed on the previous slide. At this point, we were quite ecstatic to realize that we had used computation to predict an experimental result. Moreover, because this first molybdenum bismuth binary intermetallic forms in the copper dialuminide structure type, there's a lot of literature to draw on to contextualize these results. And so I'll direct your attention to a series of Pinga and coworker papers from the 1970s if you want more details. But in particular, it has been emphasized the importance of the heterobiometallic interactions in the structure type. And so I'm highlighting the shortest distance here, molybdenum bismuth distance here, comparing that to the radii of the metals at this pressure. You can see that this is quite a bit shorter, suggesting a significant and unique metal-metal bond. Similarly, the bismuth distances are also quite important for getting this structure. And so you can see the sum of those radii down here. I compare it to the shortest bismuth distance here and the second shortest bismuth distance here. And so that I don't have to keep saying that, let's just call it D1 and D2 for the rest of the talk. You can see that D1 is quite a bit shorter than the sum of those metal radii, but D2 is quite a bit longer. And so that was somewhat surprising because another way to think about the structure is from this view here, which we get by rotating the structure about 45 degrees to the right and tilting it into the plane of the screen. You can see that in this case, the bismuth form planes in which you have interlocking hexagonal nets. But because of the distortion of D1 versus D2 in our structure, we've broken up those hexagons such that we're left with stacked bismuth dimers. And as I mentioned, this is somewhat unusual for the structure type, but it's not unprecedented. It has been seen before for the antimonide versions of the structure, so the element that's directly above bismuth in the periodic table. And given sort of that similarity of where we're looking on the periodic table, I was wondering if something electronically driven was occurring. And I think that idea is best captured if we plot D1 versus D2, which in an ideal version of the structure should be all the way up at 1. But in the case of the titanium antimonide version of the structure is down below 0.85. And as we add electrons by moving across the periodic table from titanium to vanadium to chromium, we see that the distortion lessens. And if we expand our focus to the bismuth versions of the structure, we see that the trend holds, with molybdenum bismuth being the most distorted version of the structure compared to the manganese bismuth and iron bismuth versions of the structure, which have been previously reported at high pressure, as I mentioned on a previous slide. And so this is quite interesting because oftentimes the structure is discussed in terms of somewhat strict steric tolerances. And so seeing the importance of electronic on the resulting structure, I was wondering why this might be the case. And to get at that information, I have been fortunate enough to collaborate with the Rondinelli group at Northwestern. In particular, I worked with Nathan Kucher, a wonderful graduate student there, who helped me interrogate the electronic structure computationally of my new experimental phase. Here's this density of states diagram that he generated for the structure, which is in a lot of ways exactly what you would expect at your Fermi energy, separating your occupied from your unoccupied states. You mainly have molybdenum 4D character, although there's also a fair bit of bismuth 6p character in some of the valence states as well. But I was drawn to the fact that at about 1.4 electron volts below the Fermi energy, there is a minimum in the density of states, which is often called a pseudogap and has been implicated in the observance of such structural distortions. In which case people are drawing on a second order Jahn-Teller-like effect in which you are stabilizing bonding states at the expense of destabilizing antibonding states that leads to this breaking of symmetry, if you would, in your structure, as well as this signature in the electronic structure as well. I think more evidence for that is gained when we look at the crystal orbital Hamilton population, in which we assign bonding and antibonding character to these states and then localize it towards relevant interactions. And so if we just focus on the D1 interaction between bismuth and bismuth, we can see that indeed the pseudogap roughly corresponds to a transition point from occupying bonding states to antibonding states. And there's a couple of important implications for this, which we can test to see how well they hold. One of which is that we would expect the greatest amount of distortion to occur when the Fermi energy and the pseudogap coincide, in which case we're occupying the least amount of antibonding states. That's equivalent to taking electrons out of the system or moving to the left on the periodic table. And that helps to explain why the titanium antimonide version of the structure is the most distorted. And indeed, when we look at the density of states for that structure, the Fermi energy almost exactly coincides with that minimum in the density of states. And so, as you might expect, as you move to the right on the periodic table, not only do you lessen the amount of distortion, it's important to realize that you actually start to occupy antibonding states sort of across the board for all the relevant interactions in the system, including the molybdenum-bismuth interaction, as well as the molybdenum-molybdenum interaction. And so not only does that change the structure you would get, I would expect that to also influence the stability of the phases that we're accessing. And indeed, that helps to explain how by the time we get to the manganese and iron versions of these structures, those phases are both predicted to undergo magnetic phase changes to help to alleviate some of that instability at the Fermi energy. In comparison, by shifting our focus to the 4D transition metal series with molybdenum in which we would not expect to find such magnetic distortions, I think we've identified something of a limit in accessing this structure type in this phase space, something that I'm excited to continue to explore computationally and experimentally as well. But of course, just to shift gears a little bit, that's not the only type of stability we're interested in the system. It's also important to think about kinetic stability and whether or not we can recover such new phases to ambient conditions. And the short of it is that we can't, doing the experiment in which we track how this material responds as we decrease pressure in our diamond anvil cells, while we maintain the phase down to about 8 GPa, we no longer see diffraction peaks corresponding to it by the time we get to ambient conditions. And in some ways, this is a challenge because it means we can't study these materials, can't hold these materials in our hand and study them at ambient pressure. But it's also not surprising because this is exactly the same behavior that we observed in the manganese and iron analogs. And so once again, I was wondering what type of insight we could gain from the fact that we now see this behavior so commonly. And so once again, in partnership with Nathan Kuchar from the Rondinelli lab, we interrogated the dynamic properties of this material by looking at the phonons dispersion diagrams. And so this, in comparison to the thermodynamic properties that I was showing you at the beginning of this talk, this looks at how small changes in atoms and lattice influence the potential energy surface. And so what Nathan found was that while our high pressure molybdenum bismuth 1-2 structure is dynamically stable, as he decreases the pressure in his computations, he introduces multiple points of instability at multiple points of our decompression. And indeed, by the time we get to the hypothetical version of this structure, we now see multiple imaginary phonon frequencies, suggesting that helping to explain why we don't recover this material to ambient condition. But in fact, there's a lot more information to be gained from this type of analysis. And so Nathan looked specifically at the nature of these distortions and what they did to our structure, both by themselves and in combination. And in doing so, he discovered a new molybdenum bismuth polymorph that is dynamically stable. And it's very, very similar, of course, to that copper dialunite structure type I showed you previously. It's just slightly lower in symmetry, but the differences are telling. We still maintain those important bismuth D1 interactions, but they now rotated relative to each other. And so that introduces kinking into our planes of bismuth hexagons, helping to alleviate some of the bismuth-bismuth repulsions that are introduced as bismuth grows in size upon decompression. However, also notably, we notice that molybdenum is also moving in response to the decompression. We are creating a Pyrels type of distortion into our chains of molybdenum, which were initially at high pressure equally spaced, but by the time we get to this polymorph, we now have alternating long, short distances, both along the z-axis, as you might expect, but also sort of in this direction as well. All of which is to say that we have identified a new molybdenum bismuth intermetallic that, of course, I didn't find it in my thermodynamic exploration of this phase space, but we predict as belonging on the convex hull, but we do predict that it corresponds to a local minima, and therefore is a really promising potential target if we can carefully control the amount of kinetic energy we introduce to the system as we decompress it for isolating a sample of molybdenum bismuth 1-2. With that, I'd like to wrap up, and hopefully this talk gave you a sense for the immense promise of this combined approach to really give us some deep insight sort of across the board on our materials discovery effort. Not only did we discover a new molybdenum bismuth phase, in the introduction to this talk, I really focused on the power of bismuth to lend itself towards interesting properties, but to complement what we found in these materials was that the transition metals also played a big role in the type of properties we were finding from sort of the structural electronic correlations as well as the dynamic properties. And so going forward, I'm interested in seeing how we can use that transition metal identity to gain further synthetic control in the system. And so with that, thank you once again to all my co-authors and my colleagues, Dana Friedman and Steve Jacobson, for their support, our wonderful collaborators at Argonne, CDAC again, once again for hosting this seminar and supporting our research, and you for your attention. I'd be happy to take questions if I have some time.
Okay, if there are any questions, then please unmute yourself, or you can add them into the chat box. Allison, I have one question to start off with on your synthesis. When you were doing your ball milling sample preparation, were you doing that in an inert atmosphere, or were you able to do that on the bench top?
I explored both of those possibilities to ensure that that was not operative in our results. And so I have done purely air-free synthesis of the whole process, including ball milling in the glove box and loading the diamond anvil cell in the glove box. as well as doing this in air, and I have not noticed any difference in our high pressure synthesis results.
Really? Yeah, that's interesting.
I have a question, if there's time. Very nice presentation. The prediction at the very end of the new phase that came from the dynamical instability of molybdenum dibismuth, did you actually obtain a crystal structure optimization in the calculation? And secondly, was that one of the structures that appeared at higher energy above the convex hull? It wasn't quite clear about that.
Yeah, so those are both excellent questions. So those are geometry optimized structures, I think, while maintaining unit cell parameters. And so it's not entirely free convergence, but it does maintain those pressure conditions.
Do you have a space group for it?
So it's the I4/m space group.
It stays in the same space group?
Yeah. And actually, there was a couple. So that was the most stable of the structures that we found. There was a couple of actually quite related structures. There was a CM phase. So there that was quite similar to it, just had a slightly different period to its Pyrelis distortion of the molybdenum interactions. And so I think there's a couple options there. And while I didn't find these phases necessarily in my random structure searching, so they might be, they might not correspond to large regions large regions of phase space. When I go back and plug them into my into my geometry optimization steps and into the convex hull, I see that they are higher in energy than the convex hull at 0 GPa and any of the GPAs, and any of the pressure conditions I looked at. And so what I think is happening here is that we are very close to that higher symmetry phase, and as we decrease pressure, which is why we might not find it in our high throughput approach, but as we decrease pressure and sort of they get closer to each other, so that it is, I'm hopeful, possible to sort of fall into, if we are very careful, what might be a somewhat shallow potential energy minimum of these new phases.
Okay, thanks.
In your electronic structure calculations on that I4/m phase, when you observe the alternating short, long distances, were you able to trace that back to sort of the qualitative idea of a half-filled band situation, the instability of that electronic state, or did you not go that far with it?
That's a really interesting question. I don't think we quite got that far, but I have looked at the resulting density of states for the I4/m structure, and you've lost the pseudo gap. It's not as prominent, basically, and so I think that is speaking to the fact that you've alleviated some of, maybe not. I haven't pinpointed it to the Pyrelis type distortion, but I think it does speak to an alleviation of some of that instability electronically as well.
Yeah. Okay, thank you. Are there any further questions for Allison?
I see Sarah.
Yes, if there's some time, I can ask a question. Thank you.
Yes, please go ahead.
Thank you. Thank you for the presentation. I just wanted to ask about back to that mechanically unstable phase that you observed. And in the inset, I saw that you looked at the photon dispersion at higher pressure. So is this phase, once you calculate the dispersion at higher pressure, do you see it become stable, mechanically stable?
So sorry, just to recap. So this inset is reflecting the higher symmetry phase, and so we didn't go back the other way, starting from this phase, which is dynamically stable and increasing pressure. But as I said, I looked at the pressure-dependent thermodynamic properties of this phase as well, and we don't find it on the convex hull at any point in our analysis.
I see. I see. Thank you.
Any further questions for Allison today? Okay, well, if not, then let's thank our speaker again. Thank you, Allison, for a very nice talk on describing your work for us today. Thank you. Okay, Alex, can you share your screen?
Absolutely. Right. There we go. Are you seeing the right screen?
Okay. Okay, our second half of our seminar today will be presented by Alexandra Tamerius. Alex is a graduate student at Northwestern and is close to completing her degree. She is exploring a variety of high pressure techniques, in particular for the synthesis of lead-containing intermetallic phases. She received a bachelor's degree in chemistry from the University of Wisconsin-Madison, where she combined solid-state synthesis and crystallography with computational studies of structurally complex intermetallic compounds. She also completed her undergraduate career with certificates in physics, leadership, and classics. Alexandra holds a certificate in management for scientists and engineers from the Kellogg School at Northwestern, and has also been very active in the professional development side of teaching through the Searle Center for Advancing Teaching and Learning. She's been a graduate student teaching fellow and has also served in the teaching assistant training program as a workshop designer and leader, as well as the teaching as research project. She has also participated in a variety of educational outreach efforts to local communities. Alexandra will be joining the faculty of Marian University in Indianapolis this coming fall and will continue her materials research in the undergraduate setting. Today, Alexandra will talk about the formation and stability of nickel-3 lead-2. Welcome, Alex.
Thank you very much. Thank you so much for that very kind introduction. I'm delighted to be here and to be following my wonderful lab mate and collaborator, Allison. So today I want to talk about the formation and stability of nickel-3 lead-2. And this material was particularly exciting to me, but more broadly than that, high pressure is really exciting to me because it's an opportunity to change chemical heuristics. So we can look at differences in size, we can look at differences in electronegativity and bonding, and we've seen some really wonderful talks in this series, and there will be more to come, and some of my favorite things to hear about are exotic reactivity. So things like exotic sodium chloride phases, or making new phases with the noble gases, or the really, really promising superhydride superconductors. So that's one of the things that I really, really love about pressure. But one of the challenges is what materials are stable down to ambient conditions. And perhaps a classic example of a high pressure material that is recoverable to ambient conditions is diamond. And diamond is thermodynamically stable at higher pressure in that it sits at the bottom of this potential energy well here. But at ambient pressure, it actually is metastable, meaning it's not sitting in a global minimum, it's sitting in a local minimum. And one of the things that I'm really interested in is why is this material stable? And part of the reason is that it has these sp3 bonds that help stabilize the structure upon decompression. And I'm really interested in looking at the transition metal lead compounds for a variety of reasons. One of them is that there's not that much reactivity in this space. And so looking at finding new materials here will provide us an opportunity to learn a lot of fundamental information about reactivity and bonding. And also, it's, as Allison alluded to, these heavy elements have the propensity to give rise to pretty exotic properties when we combine them with transition metals. And I decided to focus my attention on the late transition metals because we have quite a few known examples in the second and third row transition metals that we can compare our results to. And so I've decided to focus my attention there. And at the beginning of my PhD, the first place I started was with copper and lead. And copper and lead, at pretty low temperatures, they become miscible liquids. And so my hypothesis was that when you go to high pressures, that might enable you to form new compounds. And in fact, one of the things that I found was that you do form a compound, but this compound is dependent on the phase transition from the FCC lead to the HCP lead. So the structure only forms once you go above that phase transition. And if we think about the formation of these compounds, what we see is if you start with the lead HCP lattice and you expand it by about 2 angstroms in the AB plane, and you can stuff it with copper, and that copper can come from the octahedra in the FCC copper elemental structure. And so the relative sizes of these elements I discovered was really an important part of what's going on here. And so what we see though is that you have a decomposition of this phase as you decompress. So this phase is almost stable at ambient conditions, but at room temperature over the course of a few hours, it'll start to decompose. And the way I think about this is that you have a big difference in the expansion of these two elements as a function of pressure. So you can imagine that just as we formed this phase by expanding the lead lattice, as the lead lattice then shrinks, you will expel the copper back out of the structure. So I decided to go back to the drawing board and move on to nickel. And one of the reasons why nickel was so exciting to me is that there's quite a bit of reactivity with the nickel heavy main group elements. And in particular, there's this B-type family of hexagonal nickel main group compounds. And these can accept quite a wide range of radius ratios. And this has to do with structural flexibility. So I'm going to walk through some of the structures that are formed here. So in the 1-to-1 type, we have it's called the nickel arsenic structure type, but it's actually formed with arsenic, antimony, and bismuth. And then if you start removing some of the nickel atoms in the central every other layer, you get to the structure that's adopted by selenium and tellurium. And if you go all the way to the other side and start adding in an additional nickel site into the structure here, then it's adopted by the aluminum, gallium, and indium. And you may have noticed that I skipped right over the silicon, germanium, and tin structures, and that was for good reason. These structures are pretty interesting, and they form a lot of modulated structures. And so I was particularly interested there. And my favorite nickel lead is not actually present in the known compounds, which is consistent with what we saw in the thermodynamic phase diagram. So our approach for this was using high pressure, which, as Allison mentioned, is perhaps not surprising given the purpose of these talks, or the context of these talks. But for these experiments, since I was interested particularly in the recovery of these materials, I chose to use a multi-anvil press. And one of the sort of hallmark features of the multi-anvil press is that it allows us to scale this reaction up to much larger volumes. And so quickly, what happens here is we have a ceramic octahedron that sits inside of truncated cubes, and we put little strips of boron nitride in our gasket material to act as an X-ray window. And then that goes inside of the press, and I've worked with the wonderful folks at NSLS2 and at the APS to do these syntheses. And inside one of these octahedra, one of the modifications that I needed to make here was to decrease the sample size. So normally this sample space is taken up by a large, about 2.5 millimeter pellet. I needed to decrease the size of that pellet in order to get X-rays through here. But otherwise used sort of the standard setup available from Compress. And then I was able to do some in situ X-ray diffraction. And this is one of my absolute favorite days in lab, is watching the formation of a new material for the first time. And what you'll notice is here is the major lead peak that we're watching. You give it just a little bit of temperature and we start to see growing in of our new phase. And that new phase really takes off once you get to the lead melt here. And so it will continue to grow once you get past lead melt, and then upon thermal quenching, that phase sticks around. And the new phase we can index to a P63 over MMC unit cell, which is consistent with what we see in the B8 structural family. We also then decompressed this, and these diffraction patterns there are fewer of them because we're dealing with realigning the entire 1,000-ton press in the X-ray beam. But we do see that this phase continues to stick around, and here is the major peak there for that phase. Since we saw that this material forms very readily after you reach the lead melt, one of the things that I did was put in a slight excess of lead in order to do a flux growth for this material. And so what a flux growth means for those of you who don't know is that you are using the liquid metal as your solvent. And so we're doing this at high pressure, is using the liquid metal as our solvent. And since we're no longer running X-rays through this material, through this cell, we can scale up the sample to on the order of a couple millimeters. And what I'm showing you here is the ambient pressure recovered pellet down to ambient pressure, ambient temperature. And we have regions of elemental nickel, regions of elemental lead, but we also have mixed regions of both here, and they're color coded in these maps. And one of the interesting things that I noticed from looking at this is to prep these samples, you need to sand the surface of them. And the elemental lead ended up with silicon from the sandpaper material embedded in the grains, but the much harder intermetallic did not end up with the sandpaper embedded in it. So what I was able to do then is this pellet is very malleable. You are not able to grind this material. Lead is very similar to cold butter in texture. And so when you hit these pellets, you can actually eject the much more brittle crystals of the nickel 3 lead 2 out of the malleable pellet and end up with these beautiful single crystals here. From those single crystals, I'm able to determine the structure, and the structure, although related to the P63 over MMC B8 type, it is actually a modulated structure. And this modulated structure is best understood in comparison to the known B8 type compounds. And so this is nickel 2 indium. Nickel 2 indium has these chains of nickel, and then alternate hexagonal nets with alternating nickel and the main group element. In the nickel 3 tin 2, or sorry, the nickel 3 lead 2, this structure is this nickel site is half occupied. And so we have a half occupied, so it's absent, absent, present, present, absent, present. Whereas in the nickel arsenic structure, that site is completely absent. There are no nickels present in the main group layers. And what we can see from this is that there's a decrease in the nickel content with the increasing main group valence. So it fits right into the trend that we saw at the beginning of this talk. But the really exciting thing about this is that the structure is stable is metastable at ambient conditions, meaning that we can extend our intuition from ambient pressure up to our high pressure syntheses. And one of the things that was particularly exciting to me was that this structure only decomposes once you heat it up to the lead melt. So we made this material at the lead melt at high pressure, and this material will stick around even upon heating and only decompose once you've reached the lead melt again. For completeness, I also included the formation enthalpies here, and at ambient pressure, this phase has a positive enthalpy of formation, indicating that it is in fact a metastable phase. So what is driving the formation of this phase? And so to answer that question, we started looking at XAS. We were interested in the charge transfer here. And what we noticed is that there is a partial charge transfer from the nickel to the lead. So instead of thinking about this as a plumbide, it is actually a nickelide, but it is only a fractional charge transfer. This is still strictly an intermetallic compound here. And so we see that the lead is shifted to slightly higher in energy, and this shifted to slightly lower in energy, and the nickel is just slightly higher in energy, suggesting this charge transfer. And we also see, looking at the density of states for this material, that there is predominantly nickel D and lead P, and which means that there's going to be the opportunity to have some overlap and some bonding there. And then, just out of curiosity, one of the things that I wanted to do was look at the projected charges for this structure. And so this is a theoretical technique for identifying how you assign the electrons between the different elements in your structure. And in comparison to the elemental structures, what we see is that we have lost some nickel electron density and gained some lead electron density. So this is also consistent with our picture of charge transfer. And then in order to do an apples to apples comparison, we created the theoretical 2-to-1 nickel lead structure, and noticed that there is more significant transfer from the nickel to the lead and less significant transfer from the nickel to the lead in the theoretical 1-to-1 structure. And this suggests that there is something fundamentally going on here, and that even though these are not ionic compounds, our chemical intuition for a more significant charge transfer when you have a lower main group valence, meaning you need more electron density from the nickel in order to complete your valence electron count, is that we're seeing that trend across the series. So that was particularly exciting to me. And in other words, we have a decreasing electron transfer in the main group, meaning we have a decreasing nickel content with increasing main group valence. You need fewer electrons to complete your octet. So it was pretty exciting to me that held true as you explore the different pressure regimes. One of the final things that we were interested in looking at here with these materials is this material can be recovered down to ambient conditions. So what might its properties be? One of the first things we did was look at the band structure, and we noticed that there are some pretty interesting band crossings for non-trivial topology. And although this Fermi surface is not a clean Fermi surface in the sense that there are many, many, many bands crossing this Fermi energy in addition to our non-trivial crossings, we think that continuing to investigate phases in this family could help reveal strategies for cleaning up the Fermi surface for non-trivial topology. And in fact, some of the higher symmetry structures do indeed of the other B8 type compounds do indeed have slightly cleaner Fermi surfaces. So that's an area that I'm hoping that our group will explore at some point in the future. So today I told you a little bit about my investigation of the structure formation of nickel 3 lead 2 at high pressure. We'll cover the recovery of it at ambient conditions and the isolation of large single crystals, and how the bonding in nickel 3 lead 2 plays an important role in its stability down to ambient pressure. So with that, there are so many people I would love to thank for this, for help with this work, particularly the Friedman Lab, current and former members, the fantastic beamline scientists and theoretical chemists that I work with, Professor Steve Jacobson, who's been a wonderful mentor and is a member of CDAC, and thank all of you for your attention.
Okay, thank you very much, Alex. Are there any questions for Alex at this point? If so, please either unmute yourself or you can put your question in the chat box. I guess I'd like to go back to your copper 3 lead compound at the very beginning. Did you do the same kind of population analysis, sort of charge analysis on that compound as well?
So I haven't yet gone into so do you mean the projected charges, or do you mean the XAS type analysis?
The ones, the calculated charges.
Yeah, so for the calculated charges, I didn't have sort of the one of the reasons why I was really excited about the nickel is that it's part of this series of structures.
Right.
So I would have to think really carefully about what other related structures I would want to compare it to. But no, the short answer is no, not yet. But it's something that I'd like to go back and revisit for sure.
So it would be kind of interesting to note, I mean, you have those copper octahedra there, whether in fact you could do a sort of Wade's rule analysis of that part of the structure, and sort of whether your electron counting rules would hold up. I think I just might do that myself. Following up on that, what sort of computational method did you use, or what was the code that you used for when you did your calculations, band structures and things like that?
Yeah, so it was done in collaboration with the Rondinelli group at Northwestern, but the package that they used was VASP. So it was a DFT based, and then they used VASP. Yeah.
Okay.
And I believe we were using the PBE functional for that.
Okay.
Yeah.
All right. Thank you.
I had a short question. So
Yes, please go ahead.
Yeah, great talk. At one point you mentioned modulated structure in the nickel lead. Did you recover a single crystal and do a modulated, or did you see modulation in the experimental diffraction? Is that right?
Yeah, absolutely. Wow. Yeah. So thank you so much for asking that. Yeah. So the structure is both positionally and occupationally modulated, and so there's this when I talked about the structure being half occupied, but that nickel 2 site being half occupied, there is a modulation in that you can either draw an 8, 5, 16 supercell, or you can draw a 4, 4, 5, 4 primitive cell with the modulation. So it's commensurate. Okay. It's commensurate. We didn't see much of a difference in the refinement between the commensurate and the incommensurate. It was very, very close.
Okay. We just saw the satellite peaks. Wow, that's really cool.
Yeah, and then there's a slight distortion whenever that nickel site is unoccupied, sort of everything collapses to fill that void space.
Okay, thank you.
Mm-hmm.
Alex, what is the sort of effect of pressure on the melting point of lead?
Yeah, so we're actually on a great slide for that. So the melting point of lead goes up as a function of pressure, and so we've got here. This is the temperature pressure phase diagram for elemental lead.
Oh, okay, I missed that. Sorry.
Yeah, no, I should have labeled it better than I did. My apologies. But yeah, so the melting point goes up, and so in the nickel synthesis,
so definitely steep
out here.
Yeah.
Yeah.
Okay.
And so we got up above that melting point, and that's when we really saw the structure take off. Whereas the copper 3 lead structure is forming just above this phase transition, and it forms below the melt. It's forming when you're in the hexagonal structure.
Do you know if the phase diagram for tin is similar to lead in that way?
The pressure dependent.
Yeah.
Melt. So I would imagine so, because typically you get an increase in the melting point as a function of pressure, yeah. But I don't know the details of that one off the top of my head.
Okay, are there any further questions for Alex? Okay, well, if not, I'd like to thank you both, Allison and Alex, for beautiful talks today. Thank you for sharing your work with us, and best wishes on your future endeavors. Hope to hear more from you in the future. Thank you.
Thank you so much.
Thank you.
Thank you.